Welcome to 24 Hours of Past, Growing Our Community. We're excited you could join us today for Maxwell Myrick's session, The Art and the Science of Designing a Mission-Critical SQL Server. This 24 Hours of Past event consists of 24 consecutive live webcasts delivered by up-and-coming speakers and experts from the past community. All sessions will be available next week on 24hoursofpast.com. My name is Andrea Allred, and I blog at royalsql.com. I also attend SQL events in my large collection of princess dresses. I have a few quick introduction slides before I hand over the reins to Maxwell. He will speak for 40 to 45 minutes, and then we'll move on to the Q&A, where you can ask any questions you may have. Could you move to the next slide, please? If you're having any issues, just type your question into the question pane on the GoToWebinar control panel, and someone will assist you. To maximize your screen, use the Zoom button located on the top of the presentation window. Feel free to enter your question in the Q&A field at any time. The questions pane is located on the right side of your screen. Once we get to the Q&A portion of the session, I'll read off your questions to the speaker. Since all the attendees are muted, you will need to submit questions by typing in the Q&A field. Note that there will be a short evaluation at the end of the session. Your feedback is important to us, so please, please, please take a moment to complete it. It will show up on your screen. Next slide, please. I'd like to take a moment to thank our presenting sponsors, Microsoft, Cisco, and Dell Software. In addition, I'd also like to thank the support sponsors for this event, SQL Sentry, HP, and SolarWinds. The staging of 24 Hours of Past would not be possible without their support and dedication, and they are the reason this event is available free of charge. Next slide, please. Next, I'd like to bring your attention to the upcoming Past Summit, taking place in Seattle, Washington from October 27th to the 30th. Past Summit 2015 will feature over 200 sessions of world-class SQL Server experts, planned and presented by the SQL Server community for the SQL Server community. Past Summit is single-handedly the largest gathering of SQL Server and BI professionals. With over 5,000 attendees from all over the world, Past Summit is also a great place to network and meet face-to-face with experts, peers, and MVPs. More importantly, Past Summit delivers on providing you with the answers to your SQL Server issues, along with the knowledge, strategies, and skills you need to stay ahead of the curve. Contact your local chapter for a discount code to save $150 off. Optimize your savings by registering before the end of Sunday, July 12th. To find out more about Past Summit, visit www.pastsummit.com. Next slide, please. And now, please allow me to present the speaker of the hour, Maxwell Myrick. Max is a 15-year Microsoft veteran, which includes 5 years on SQL Server development, where he ran the SQL Customer Lab, and then the Sustained Engineering team. He was an initial member of Microsoft's Mission Critical team, where he has worked directly with some of the largest SQL Server applications worldwide for 8 years. Max was also a regular speaker for Microsoft at TechEd and TechReady, as well as the creator of several new service offerings, including the monthly hotfix report, which is awesome. 2 years ago, he joined SQL HA, where he continues to work on mission-critical system design, implementation, and support. Next slide.
Thank you very much. So welcome, guys. Basically, what we're going to cover today is mission-critical systems. We all kind of know what these are and kind of don't know what these are, but this is going to be kind of a holistic view. My goal is to give you the building blocks so that you can look at your needs and say, this is what we want to accomplish, and map that to features, and not so much just say, hey, here's the high availability feature, let's implement that, that'll meet all our needs, because sometimes it doesn't. There's a whole bunch of different ways of looking at this, different levels of mission critical. What I'm going to do is I'm going to cover really all of them, top to bottom, everything that you have at your disposal, and really try to give you the understanding of that. I'm not going to go too deep on implementations. I really want you to understand how they fit together so you can pick and choose what works best for you. But that doesn't mean we're not going to get a lot of best practices. So on pretty much every slide, I think in this deck I've got about 30-something right now, really try to give you some actionable things that you can go use when you're doing this about what is going to make this really work, what is going to make this really fail, so you can watch out for that. What are the things that's really going to make a difference to you when you're doing it? And then the last thing we're going to cover in here is some of the, I call them supersized mission critical applications. Not a lot of people have gotten to work with these. They look and act, they're designed and built completely different from kind of the normal SQL Server world. And so I'm going to expose that, basically how you, as you're building out, partitioning, scaling out, how you get to these systems that are several hundred physical servers performing, one action that runs something for an entire country or even for multiple countries. So hopefully you'll enjoy that. That having been said, let's start off with mission critical system. Everybody has their own definition of mission critical system, and it's a very mushy thing. The main thing for you to remember here is that it is a mushy thing, and just let that be. The example I give here is when you are having to work late to bring that server back up, your manager is very clear that this is a mission critical server and you have to stay all night. And yet the next week when you present a request to get some new hardware that would have prevented that outage, suddenly that system is not so mission critical anymore. We've all been there. Instead of fighting that, my recommendation is to compete like water. Today in the session, you are going to see all kinds of different ways to add availability and disaster recovery to keep these systems up and make them better. Just embrace the fact that your management will not be able to embrace all of them. It will not support them. Some have different kind of money, like maybe they have money for hardware, not for software. Maybe they have it for dev and not for this. Just think of it in terms of where can I add value to the system? Where can I improve the system I have today? That's the main thing. When we look at this, that's going to be hardware redundancy, it's going to be server redundancy, it's going to be application redundancy, kind of three different levels, three different places where we can make these systems much more robust, increase our uptime. Told you I had some best practices filled in. Here's your first one. I just used the word redundancy. When you are talking to upper management, using the word redundancy can be bad because they have just been trained from birth to eliminate redundancies. That's extra cost. And that's not true when you're talking about mission critical systems. When you say we have redundancy in this hardware or in this site, what you're really saying is we can survive these types of outages without people noticing. So you may have to work to re-educate certain levels of management that redundancy is all about mission critical systems and availability. If you can't do that, just avoid the word. Phrase it a different way, but be aware that that little landmine is waiting for you. If you were to send a proposal up to add redundancy to a system, you'd eventually hit one of those guys. And when you're having the conversation with them, it's not nearly that bad. All right. Hardware is something we kind of have to talk about just because it is getting less and less notice these days. With all the virtualization, with the cloud, with the silos in the work environment, the people who work on the hardware not necessarily touching to everyone else. Primarily as DBAs, we actually have to circle back around and focus on this again. And so if you've done hardware ordering for a database system, that's great. You kind of know all this, but just remember it starts with the server level. When you talk about kind of server level hardware versus, say, a desktop PC, really what you're talking about is a few things that make that server, that harden that server, that give it a lot more uptime. Like, for example, redundant power supplies. This is where your line voltage comes in. It has to handle any of the spikes. Most machines have one. These mission critical servers, they have two. And if either one of them goes down, the other one supplies 100% of the power. A lot of them are even hot pluggable, so they're fantastic. The second thing is RAID. You probably know about RAID. That is, if a disk fails, well, we've got some kind of parity or we've got a mirror, so a disk going down no longer hurts us. There are a lot of distributed storage models now becoming very popular with the cloud. Doesn't matter the implementation. What you want to say is, if a disk goes bad, do we continue to work, even if it's lower performance? A really important one is ECC memory. Now this is just parity for RAM. Literally it's a ninth IC instead of just 8 ICs on the DIMM, the standard implementation, and it works just like RAID 5 parity in all honesty. One of the main things about ECC memory is it can detect a problem. So the way it works is if the parity bits don't match up, then it begins to say this sector of memory is bad, it just maps around it, stops using it, so you have a little bit less memory on that system, but you keep right on rolling. Now if you think about what that means for systems without ECC memory, it means that you don't have that check. So therefore, either you're crashing or worse, you're corrupting memory and you just corrupting data because it's getting corrupted in memory before it's flushed to the disk. You just have no way to know. So ECC memory is very important. That's the way you kind of double up there. When we talk about the network, most of your network cards or HBAs going out of your machine have 2 ports. But if that network card or HBA goes bad, what are the chances that it's only going to go bad on one of the ports? The reality is the whole card's probably going to go bad. So yes, it's more expensive to buy 2 cards, but then if either of the cards goes down, then the other card is still working. And hopefully you are presenting that all the way up to the switch level. If you want to have 2 cards, you have 2 cables, or even 4 cables, no reason not to connect all 4 ports. You can get more bandwidth, and you can also have more reliability, but connect those to different switches. If they all go into one switch, again, you have the single point of failure. All right, few best practices right here. A lot of people don't think about it when they're buying the hardware, and especially when they're getting the budget for the hardware, but it's a great time to get spare parts, especially in the modern world. If you wait 2 years and then you need a replacement drive or replacement memory or replacement processor, that can become a very constrained product. It can be very difficult to get. So if you buy some spare parts up front, you don't need many, just a couple, one of each, one extra power supply, one extra hard disk, one extra set of memory DIMMs, it can make a huge difference. It actually helps you in a couple different ways. First of all, if one of them fails, you've got a spare set right there in the cabinet. You plug it in, like if it's a disk, the RAID begins to rebuild, you're back up and running, and then you cross-ship that with your hardware manufacturer to get another one back in. So you get back up and running immediately. The other thing is it's a nice way to troubleshoot. If you think memory's going bad in a machine, really the best way to troubleshoot is to reach in the cabinet, pull out a pair of DIMMs that you know is good, put those in, and if the machine suddenly starts working, you're pretty sure the memory's bad, cross-ship it back to the vendor, right? We talked about buying those multiple network cards and multiple switches. If you're doing that right now, be aware that it's a great time to upgrade your network speed. We got a lot of SSD technology, especially in SANs and NAS. Today they often have 20% SSD. Memory size is going up. A lot of the systems I work with have 512 gig of RAM. Talking massive SSD to RAM, you're going to need your network speed to keep up. So consider investing a little more in network right now. And the last one also related to those SSDs, if you're not familiar with that technology, they have a limited write life. You can read from them all day, but when you write to them, every time you write to them, it's like you use a little bit of their lifespan. And they track this, they know it, it's pretty well documented. The main thing about this, again, going back to budgeting, is your hardware might last 5, 7, maybe even 9 years. Your SSDs on a SQL server, especially the ones under tempdb in the log where you're writing like crazy, they might only last 2 years. So you need to plan for that. Right? I'm not saying that you buy a whole bunch of them up front. SSD technology is moving very rapidly, so that's a place where the SSDs you'll get 2 years from now will be much better, but you want to go ahead and budget for that. Don't think we're going to buy all this hardware and the servers and the SSDs are going to last 7 years, because where you're using those SSDs really heavily, they're just not going to last that long. Plan ahead. All right, all these are ways to keep the server up, right? Individual components within the server go bad. The server has duplicate components, so therefore it keeps right on running. But eventually the server will go down. Eventually we'll have some kind of problem, operating system, memory leak, application, whatever. And we get to the type of redundancy that most people think of. This server redundancy, this failover, if you will, most of the time when people think about mission critical systems, this is what they're thinking about. They're thinking about server redundancy. They're thinking about some kind of server level failover and the features related to that. So that having been said, this is the one that most people are familiar with. A couple things I want to cover here, though. There are actually 2 different implementations. One used to be a lot more common, and that was shared memory. The old VAC systems, some of the NEC hardware out there, very nice, very fast failovers when you share memory. The most common one on the Windows platform is shared disk, so that's Windows clustering. We're familiar with that. Basically, the way these work, the machines are connected at a physical level to some resource, and therefore when either of the machines or any of the multiple machines, because you can have lots of machines in a cluster, has a problem, the other machine takes over, and that's nice, right? Just remember there always has to be a controlling entity there. The controlling entity on a cluster is called a quorum. You can think of this as if 2 machines are sharing memory or if 2 machines are sharing disk, right? How do you know which machine is the current lead machine? How do you know the one that's working right now? Who's in charge? Who gets access to the disk? The other one's basically your failover partner. It's waiting for something to happen. Lots of interesting technologies there. The main things for you to remember here, all of these different implementations of well, we'll call them clustering on the Windows platform, all of these different implementations have a few things in common. The critical thing is what is detected as a failover. So usually you have a network connection, and if that network connection to the server goes down, then everybody knows the server's down. For SQL Server, when we start talking about failover cluster instances, there's actually a little SQL ping where you can see if the SQL service is responding to the SQL ping, so it knows that the SQL service itself is in a bad state. That doesn't mean that that's 100% SQL Server. There's a lot of states it can get in where it can still respond to the ping, but it can't do your application work because you're asking it to do something specific. The point is you really want to think about, for whatever implementation you have of your server level failover, what is detected. That's what's important to you. And then based on what's detected, you need to group together the resources so everything fails over together, right? If these two servers need to be at the same site, or if they need to be co-located for network performance reasons, make sure you group them together. Those are called dependencies when you're using most of the technologies, and then they'll all fail over together, keeping everything in the same place. The last one, we have a lot of good quorum options now, different witnesses, different witness types. The main point of these is that you no longer have to be very close to the server. You no longer have to be in the data center, if you think of it that way, to say which server is up. This is especially important where you're having some network brownouts, right? You might have multiple data centers with multiple servers, and within the data center everything's working okay, but your end users can't get to it. When we talk about these kind of quorum options, these other options that you have now, be aware that you can put one of those, should put one of those, as close to kind of the end user network location as you can, because if only one of those servers is reachable by the end users, you want to make sure that wins the election and that takes over the resources. All right, that's server level redundancy, and we've begun to shade a little bit into site level redundancy. Now, sites get a lot more interesting. The reason is because within a data center, there are a lot of events which can take the whole data center out. I went through Hurricane Fran in 1996, and we had 18 feet of water over our work, and 18 feet of water will shut down your data center for a very long time. That takes a long time to clean out and rebuild. There's nothing you can do about this. When you have these natural disasters, political unrest, war, tornadoes, hurricanes, floods, they're going to take that entire site out. And the only way that you can really deal with that is to be prepared to have another site, right? Whether you're building it or whether it's already available. If it's already available, it's awesome, because then it becomes a failover, very much like those server failovers we were talking about, okay? The other advantage of those sites is you can do local processing, and that can save you a lot of latency and a lot of network traffic. Now, the challenge with the remote sites has traditionally been you've got a long network path, you got a lot of latency. So a couple best practices here. The first one is, if your company, this is really important, if your company does not have a second site today, and hopefully you do, at least as a DBA, at least get a second site set up and your backups there, right? If a natural disaster of some type hits your data center, you need to have a set of backups somewhere else. You can get hardware, you can rebuild everything else. Make sure at least you have a backup somewhere else. And then the second one is, there's a link here, talks about one of the upcoming changes in SQL Server 2014 around availability groups. We talked a little bit about that latency. A lot of times when you have a remote site, sure, you've got to keep the data in sync between these sites. That connection may not be great. It may not be a high-speed connection. It may occasionally be down. How long will it be down? A lot of the technologies that were used to distribute that data to the other sites, they wanted a rock-solid connection. And if that connection failed for a while, it was very hard to get it restarted. And they've done some great work in SQL 2014 availability groups. Have a look for that. If you're looking to do a site, now's actually a great time to make that an upgrade project and see what they're doing there. Okay, the next level is database redundancy. So all of those hardware issues about the parts within the server, multiple servers, multiple sites, these are all, you can almost think of an application or Windows or SQL as a service type level, but you also have to think about your data. And when you get to the data, you have a huge number of options. I've listed 6 here, but there are more than this. The difficulty of these, if you think about it, all has to do with a single idea. Now, some of you are going to be familiar with this. For the ones that aren't, this is really important. Every one of these implementations is the way it is and is challenging, and you need to understand it in terms of this one simple statement. There's only one copy of the truth. So let me drill into that a little bit. These are relational databases, and in the relational database world, we have transactions. They're logged in the transaction log, and the law is that if the SQL Server, but also Oracle, anybody else's relational database, if we acknowledge in the log, we actually call it an ACK, if you send us a transaction and we ACK it, we're guaranteeing that we will do it. Notice I didn't say we guarantee that we did do it. No, we guarantee that we will do it, right? Even if you take a backup and restore the backup, right? It'd be in the log, and we can do it later. If the machine fails over, then once it fails over, it's in the log. We'll roll forward, roll back. We'll get it. That has to happen. And the challenge with this is when you start getting into multiple servers and multiple sites, you have to understand that there can still only be one copy of the truth. So the example here, a good example to think of, is like a checking account. If you have your checking account and you have $500 in it, and you write 2 checks for $300 each, maybe one's for a couple months power bill, one's for a couple months internet service. Those 2 checks for $300 each total to $600. You can't pay them both, but that's not what happens. What happens is your checking account's $500. The first check comes in, doesn't matter which one it is, it pays. Takes $300 out, you got $200 left. The second check comes in, there's not enough money, so it gets rejected. If you had multiple copies, multiple servers or multiple sites or in any other way, multiple copies of your checking account, if there wasn't just one copy of the truth, right? So there's 2 locations. If one of the checks got presented at one of those locations and the other check got presented at the other location, both checks could go through. If they came in at exactly the same time, there's enough money to pay either one of those checks. And then eventually, when these machines synced their data across, there would be what's called a merge conflict, because there's actually not enough money to pay both of them. And one of them would have to be picked, and it would have to be rolled back, and then that money didn't get transferred to whoever you paid it to, and then they couldn't pay their bills, so their money would have to get rolled back, and this becomes a big nightmare. Doesn't happen in the relational world, because if we had to roll one of those back, it means we broke the law that says if we say we're going to do this transaction, we're going to do this transaction. And that's why when you look at all of these different database redundancy options, because we're talking about database redundancy here, every one of them, whether it's backup or transactional replication or log shipping, all of these are about how do we keep the transactions. We've got to keep transactional integrity between 2 sites. So just remember, there can only be one copy of the truth, and all of these, the implementation of every way to do this, has to make that statement true. That's why these implementations get very interesting when you look at the different ones and how they work. All right, I said there's only one copy of the truth. I know somebody's going to bring up two-phase commit, so let's go ahead and talk about it. Two-phase commit does not change the fact that there is one copy of the truth, that wherever a given piece of data lives, there's only one server that really owns it, and all the other servers are copies of it. What two-phase commit does is it hides that from you, from a developer level, if you want to think of it that way, and it says, I can handle this for you. But that's very much the duck that is floating placidly along the lake and underneath the feeder going like crazy, because the reality is this is having to handle the locks underneath. Standard two-phase commit, what's going to happen, you go into the remote node, the non-owning node, and it's going to have to take a lock there. Then it's going to have to go back to the one copy of the truth, the master node, the ones that owns it. It's going to take a lock there. Now, it's possible, based on what you want to change, that the data is changed. The data in the master copy might be different from the data you're looking at down here. Maybe you don't have the latest, or maybe you haven't updated. So then there has to be some kind of, has this data changed, and do we need to care? That's usually done at the application level. And then afterwards, you can make the change. You're holding these locks, and you've got a latency connection here probably between sites. So it's probably in milliseconds over a network. Can be painful. So long-held locks, that's always bad latency. Anyway, once we have both those locks, we can change it. Logically, we would change that where you are and then change it on the master, but that would be an extra round trip. And remember, these round trips are incredibly expensive in terms of time and latency, turnaround time. Time we're holding locks, which increases locking and blocking. So instead, almost all the implementations are going to change it on the master copy first, and we could be done. In other words, you only have to change it on the master copy. All master copies have a way to update their secondary copies, right? There's a way that the data flows down to there. So we could just wait and it would get down there. Most of the implementations know that users don't like to wait for that, and we don't know exactly how long it will take. It depends on the implementation. So most of them go ahead down to the wherever you did that, maybe not to all the replicas, but at least to one, and make that change. And you would think we're done, but no, we're not done yet, because remember, this is still some kind of secondary. The master is still going to send the change down here on the normal process, however it does that. So we actually have to have yet another construct that sits on this one node that we did change and says, by the way, when the master sends us this change, remember that we already did it here and don't do it again. That's what two-phase commit really looks like. Implementation varies a little bit. This is incredibly intensive. So two-phase commit, long latencies, long held locks, a whole lot of network time, not necessarily the best way to go. When we look at the best practices here, the first thing to remember about two-phase commit, lots of people like it because it seems simple. You know, we can update anything anywhere all the time, but you pay a really high cost. In trying to make a system scale, this is almost certainly just not going to scale. You put enough load into this, you're going to hold the locks too long, you're going to have too much network latency. It's going to be very painful. But that's not to say it doesn't work for everything, so it'll probably be useful for me to give you an idea of what application it does work for. Think about a online voting application. Here in America, we vote every 4 years for the president. We could have a centralized database. It's the one copy of the truth. It's the master. And we could distribute that to as many different nodes as we wanted. Let's say there's 50, one for each state, and you have a record that you can reach from any state, great, and you do your voting. This is a really good fit for two-phase commit. Let me talk about why. First reason, all the transactions here are atomic. When you go to vote, you update your voting record, right? That's it. You can't touch anybody else's voting record, and no one else can touch your voting record. So there's very little conflict here. That's important, and the transaction is really small. Go ahead, make all your selections. When you're ready, hit done. It'll sync up to the main server. You don't care if it takes 2 seconds or even 5 seconds. You kind of expect that because it's a voting app from the government, so you're not really expecting great turnaround time. The second thing is that you don't have any locking issues, right? You don't even have any background jobs. When you're touching your record, no one else can ever touch your record, not ever. There's no background job that can be working on your record. So there are no locking conflicts. There just can't be locking conflicts. That's an important thing for two-phase commit because remember me talking about holding those locks a long time begins to block other pieces of the transaction. Then this all spirals downhill and the application ceases to scale. If you have an application where the locks are atomic and there can be no locking conflicts, this is a much better fit for two-phase commit. And then most importantly, imagine you voted and then somebody else comes in as you and tries to vote. It says, nope, you've already voted, and it just ignores them. Maybe it logs them to go check that out. You know, maybe some policemen should go talk to them there at the polling booth or wherever. But the point is, it knows you already voted and you only get to vote once. And you could just as easily design the system. Maybe you can change your mind. Maybe you can change your vote up to a certain fine. Instead of first in wins, last in wins, you can come up there as often as you want and change your vote up until a date. Last in wins. There's still never a merge conflict. There's a business level logic that is always true, so the server doesn't have to worry about merge conflicts. If your application looks like that, two-phase commit, probably a good fit. Otherwise, and for most applications, that's something you want to avoid. Now let's talk about something you want to address. As bad a fit as two-phase commit usually is, reporting servers are the most overlooked and underused great fit for SQL Server applications in the world. If you don't have a reporting server, you need to go out and get one. You know, sure, there's a hardware cost for another set of hardware and disks, but this is a huge opportunity. We talk about that one master copy, the one copy of the truth. That has to do with inserts, updates, and deletes. In other words, modifications to the data. When you have a reporting server, you have a whole nother server that can answer anything that's a read. You still can't insert, update, and delete here. The one copy of the truth is on the primary server, but on your reporting server, you can take the really big pieces of traffic completely off it. That is huge. You can take their locks off of it. That is huge. You can take the I/O off of it. That is huge. A lot of easy ways to set up a reporting server. So really, this is Scale Out 101. It's a very easy thing to implement in the modern world, which is nice. Availability Groups gives it to you, and really scales well because reads do not lock out other reads. The one thing you have to watch out for with the reporting server is that a lot of people want real-time data, and most of those needs are not real. In other words, management will say, oh, I got to have real-time data, and let's say using transactional replication, maybe your reporting server's 11 to 13 seconds behind, and you go, really, it's 11 seconds behind. If you were to run this query now, as opposed to when we started this sentence, you would get that data. So when they tell you they absolutely have to be real time, a lot of times it's best just to not even have that conversation, because the people who are telling you that probably really don't understand this one copy of the truth thing. They're not database people. Just set up the reporting server, make it available for them, let them run the business analytics there. For goodness sakes, it's very powerful. Let them run their management queries there. Try to avoid the conversation about how far behind it is. That's just not a conversation you're really going to win, but make it available, and what you'll find is if you build it, they will come, and it doesn't in any way affect the performance of your production server. It's a great way to really improve the performance without a lot of cost. All right, then we get to true scaling out. So a reporting server is kind of an easy way. We made a whole copy of the data over there where we could do some read-only work. That's great. But let's say we really want to scale out. The first level of scale out, the first type of scale out you should learn, which very few people know about, is called data dependent routing, TDR. And this is just basic scale out. You split your data into multiple parts, it goes into multiple servers, and at the application level, you route the work to those servers. It's very straightforward. It's been around forever. One of the links there is to an MSN example. That's actually from 2003. In those situations, we got a couple hundred servers that we were running, and it was partitioned, we're going to talk about that word in a minute, by IP address. So each one of those servers served a certain IP address range. Very simple, very straightforward. The routing was actually done at the IP level, so at the router level. The router routed those IP addresses to the server that served those IP addresses. So really beautiful scale out. One of the nice things about DDR, infinite scale out, and no feature usage. There's not a single SQL Server feature that is needed for this, or Oracle, or anybody else, and that's why people never hear about it. You'll never hear the dev team talk about data dependent routing. It's not a feature. The SQL Server has no idea that instead of it being the SQL Server, there are 4 SQL servers, and you've split the data between them, and you're routing the work between them at the application level. It is totally unaware. As a result, it's very portable, it's incredibly scalable, it works great, but it's not a feature of the product. That's not someplace where SQL Server can say, we're better than Oracle, or where Oracle can say, we're better at DDR than SQL, because the reality is you just have to be a better database. The dev teams compete on products. They compete on features. This one, not feature-based, so just always consider this an option. All right. We talked a little bit about partitioning, so we got ahead of ourselves a little bit. Let me go back and just do a few minutes on partitioning. Partitioning is not a hard term. It just means we split the data up. What we did is we had to cut the data somewhere, so we cut the data and we put it into multiple tables, multiple servers, etc. The 2 terms you hear with partitioning are horizontal partitioning, which means we sliced it by rows. So if you think about an address book, we put the first set of names, A through whatever, in the first one, and then the second set of names in the second one. If you talk about vertical partitioning, you're putting columns. So in that situation, instead of putting all the data about the atoms in the first one, you would put just the name and phone number in the first database, and their address and some other information about them in the second. Generally, people don't talk too much about horizontal and vertical partitioning, so you won't hear people having a conversation like, oh, we decided to horizontally partition our data. This just doesn't make much sense to humans. Instead, they'll say something like, oh, we partitioned our data by customer ID so we could scale it out to 3 servers. Or they'll say, oh, we partitioned our data so we could shrink our row size and improve our transactions. That would be your vertical partitioning, for example. Make your row size smaller for one of the tables so that your I/O becomes more efficient or your locking becomes more efficient. And I would encourage you to speak about them that way. Most people, horizontal and vertical, they're not going to know exactly what those mean. Just talk about why you did what you did with your partitioning choices. Partitioning can be very important. All right, number 3, we talked a little bit about DDR. That's where you split the data up and you manage it in your app. And of course, dev teams don't talk about that. Dev teams talk about the huge group of things that are in database assisted scale out. So what do I mean by database assisted? Well, we're still going to split the data up. We're still going to partition in some way, But now we're going to use the product, SQL Server, Oracle, or whoever, to route the information to the right server. And there are a lot of different implementations of this. All right, so there's a little asterisk there to remind me to talk a little bit more about one of the names. You notice up at the top, we talk about partitioning, sharding, federated database. Let me just give you a little bit on sharding. When you partition, you've split the data into two tables. If you leave it in two tables, that's great. You could also move one of the tables to another database. Now you've split it into two databases. They could be in the same instance. That's still called partitioning. You could also move one of the databases to another instance of SQL. Now, technically, you've now crossed the line from partitioning. You have partition still. You still had the partition, but it's now officially called sharding, trying to teach you a little bit of the language as soon as it lives in a separate instance, although you probably didn't get a huge benefit from it being in a second instance until you move the second instance to another physical server. So really sharding, even though it really by definition means second instance, is usually used for different server. So you've truly scaled this out to multiple servers. That's where the term sharding is normally used. But the reality is, when you're working on these applications, you're probably not going to talk about sharding. That's not where the work happened. Once you split the data, you had to figure out how you were going to partition it, and you did partition it, moving that table to another database, the database to another instance, the instance to another server. Those are pretty straightforward tasks. The hard part at the dev level was doing the partitioning, so that's normally what you discuss. All right, so let's talk about some of the various implementations. There's a link there to a SQL Server white paper that lists a whole bunch of different database-assisted scale-out options. The most basic one is a view. Most of you have worked with views. When you think about what a view is, this is another look at the data that's down there. The one copy of the truth is still down there in the database in the table. Oh, and here's another copy that we can use, right? So this allows us to treat it in a different way. Not surprisingly, one of the first implementations on SQL Server was DPVs, distributed partition views, which I'm going to take a minute or two to talk about because this will help you understand them. Now I know a lot of people are saying, I don't want to learn about that old feature. You know, that feature is 12 years old. When you're learning about the basics of a car, it's a lot easier to learn from a Model T Ford than from a brand new Ferrari. The Ferrari has lots of features that aren't critical to carness. So let's look at DPVs. DPV basically drops a view over multiple servers. You have partitioned your data. It didn't do it for you, and you drop this view. And what this view means is that each one of the servers participating in this DPV has some idea, not only of all the other servers that are participating, but what data each one of the servers have. This is metadata. You can think of it as a little bit of index data. And then when a query comes into, let's say you have 4 of these servers. Each one has a fourth of the data. When a query comes into the first server, if that data lives on the first server handles it, just does it. I've got the data, we're done. But if the data lives on the second server, then the first server says, you know what, I don't have that, but I can do it for you. Takes that transaction, unwraps it, uses Microsoft DTC, Distributed Transaction Coordinator, creates a new transaction, goes out over a linked server pipe to server 2, server 2 handles it, passes it back to server 1, server 1 puts it back in the original transaction, and sends it back to you. All right, that wasn't very efficient, but it was very easy. And this is what we're talking about here. The reason I wanted to start with DPV, I already taught you DDR. DDR is where you handle everything at the application level. You partition it, and then you route the work. DPV is the opposite end of the spectrum. DPV is where it routes everything for you, right? From a dev point of view, you don't care where it is, you don't know where it is, you can send any data request to any server. If it's on multiple servers, it'll handle it. So that's nice. Everything else, when you look at every other Oracle rack, when you look at every other partitioning and sharding implementation out there, they're somewhere between DDR and DPV. If you understand DDR and you understand DPV, then the reality is you understand how these things work. But do you understand how to make them scale? Well, when I was on the dev team, I used to have to teach this. This is back in the SQL 7 and SQL 2000 days. In order to make a DPV scale, you have to follow this rule. It's called the 90% rule. So what that means is if you can go to the right server 90% of the time, so in that server 1 example, server 1 through 4, if you can route the work to the correct server, the server that has the data, 90% of the time, then it will scale. If you go to the wrong server, then again, it almost begins to look like that two-phase commit example. It's very expensive, high latencies, long lock times underneath. It's not going to scale. So not surprising, what you have to do is you have to go back to the application level. You don't have to do 100%. You can still, DPV is especially good where 90% of the time I can do a DDR-like implementation. I can get to exactly my right server. But sometimes I don't know exactly my right server, or sometimes it spans multiple servers. But it's only 10% of the time. Great place for a DPV in that regard, and it actually will scale. A lot of people will tell you it won't, but if you can get there 90% of the time, it works great. Always, however, though, when you're doing these scale-out options, remember that network latency is your enemy because you're going to hold locks across those a lot of times. You're going to hold transactions open across those. All of those are going to use handles within the operating system, within Windows, within SQL. It's going to make you not scale very well. So your network latency is your enemy. Put these in the same data center, put them in the same rack, give them really fast networking, optimize that. All right, so the second piece of this is, I told you that DDR scaled infinitely, and really it does. You have to understand that there is a limitation to any of these database-assisted implementations. Because the server is going to help keep up with where this data lives and route it correctly for you, obviously there's overhead. I have to have some idea of who has what to route it. And that metadata actually becomes a limiting factor. So if you ever heard of DPV squared or Coyote squared, there's an implementation there where you can have servers that only have metadata. And then down beneath them at the next layer, you have servers that have the data. That's a way to make it scale, but even that has a limitation because all the information about who has what has to be copied to all of these servers and kept synced, and eventually that becomes your limiting factor. All right, very important. When you're thinking about any of these scale-out options, your partitioning strategy, partitioning at the right point, in other words, how you slice your data so that you keep your atomic transactions, so that when you're working with one piece of data, you don't have a lock on another piece of data. When you're working on one server, on one partition, you don't have to also be working on another partition. That is what's critical. Let that be your guide to how you slice your data. That having been said, not every application can scale out. There's no question that if you can scale your application out, long-term, as the application grows, you're going to have lower costs, and long-term, as the application grows, you're going to have better availability because you can throw more hardware at it and you can throw cheaper hardware at it, and that combination can give you great redundancy, which gives you great availability. But there's some applications that don't. If you can't partition properly, then it's going to be hard to scale this out. So that having been said, it's worth having a few best practices for scaling up. When you're scaling up, parallelization is how you scale out. How many procs or how many cores do you use for this? You're going to want to watch that. You're going to want to guide that. That's your max DOP setting. Your CX packet of your waitlist types. That's going to show you when you're spending extra time there. Also, locking, blocking, and deadlocking, just as important on a big system. When I say minimize downtime here, what I'm talking about is if a SQL Server has been up and running for a long time, it's optimized the cache, it's optimized the query plans. You lose those unless you do some kind of failover with virtualization technology like Hyper-V Lab migration or vMotion. Always think about that and try to create your high availability plan so you can use a cache keeping failover option. Scale out, not surprising. It's all about how you slice that data up. What is your partitioning strategy? Making sure that you keep your transactions within that partition. Again, locking, blocking, deadlocking is your enemy, and your network latency is just going to become critical. You can almost think of these distributed systems or federated servers as being a huge computer made out of multiple servers. And when you do that, it becomes very clear that your networking between these servers and between your storage is your system bus. Virtualization in cloud, everything we've talked about here, that we've talked about generically, really applies to virtualization. It applies to cloud. When you're building these systems, you can build them virtual or physical. You can build them hybrid, you can build them on-site, you can build them cloud. How you partition these, one of the links I included earlier was the Azure Sharding link. It's got some nice technology up in SQL Azure for you, right? The main thing about virtualization in cloud is they make scale-out systems much easier by automating the provisioning of these systems. Very quick to get them up and running, very quick to attach them to their resources. Scaling is still not automatic, but If you are not already working toward virtualization of your SQL servers, I think SQL servers in general are a little bit behind the rest of the world in virtualization. You want to be heading in that direction. It's a step to the cloud, no question. It's a step to scaling out, no question. And you get a benefit today just in terms of managing your servers. So if you're not already doing some virtualization, head there. All right, we're down to the last subject, doing pretty good on time. Let's talk about this. I said we were going to talk about some of the supersized systems, these things that have several hundred servers working together. They are designed and built completely differently than the SQL servers most of us work on. And yet they use a lot of these components. We still partition them. Often they're horizontally partitioned. In addition to the level of partitioning I'm talking about here, we partition by workflow. So if you think about a piece of work that has 5 or 6 stages, we actually have servers that work on the first stage and another set of servers that work on the second stage. And they harden at the end of each stage. Everything happens asynchronously. Work moves into stage 1, then it moves to stage 2. There's a queue for each stage. You can have multiple pieces working on the same thing. So almost all of these systems are designed so that if 2 servers work on the same piece of work, whichever one finishes the work logs it. When the second one finishes the work, it just says, yep, I've already got that result. That's great. Thank you. And it just keeps rolling. This gives us beautiful scalability. It also gives us incredible redundancy. We usually have multiple servers. 4 is a nice number working on every piece of work. Theoretically, 3 servers out of 4 could go down. We wouldn't even care because 4 servers are processing each piece of work in parallel. Give you a little picture of what these look like. Looking at this picture, the bottom, you'll notice these 2 servers is a very simplified example. Both servers have everything. Then there's 2 sets of 4 servers which are either pulling or it's getting pushed. When these servers come up, they say, give me some work. And the big servers, the stage 1 servers, hand them some work. They process it, they log it, and then they make it available for stage 3. Here in this example, you've seen that we're using different levels of horizontal partitioning. Each one of these workflow stages has a completely different horizontal partitioning strategy, in addition to the fact that we have workflow partitioning, dividing the work up between these servers. And that's how these really big systems are implemented. Lots of servers working together, multiple servers doing it. We get several advantages, but one of them is a performance play. If you think about a relay race, you have a bunch of folks running, handing the baton to the next one. Your time is the worst time of each one of those people. By doing all of this work in parallel, asynchronously in parallel, using multiple servers to process each piece of work, we actually get the best time of each one of those servers. And this is a completely different concept than all of those things we talked about before we got to workflow partitioning. Because suddenly we're getting the best time of any one of those servers. And the end-to-end significance of that can be massive, especially for financial transaction servers. When we talk about hedge funds and stock exchanges, microseconds really count. So you actually get a time component, a latency benefit from designing the system, in addition to the fact that losing half your servers might not even matter. One of the other things is we might not have to restore an entire database. Restoring a database can take a long time. A lot of times we can just feed transactional data out of a log into it using an ETL task. Because it's asynchronous, it goes into the queue, it gets worked out, flies right along. Best practice there, make sure you plan for lots of application logging when you're working on a system like that. Compliance and regulatory, I can tell you, those big systems are going to have a lot of it. Plan for more disk I/O than you thought. All right. We've covered everything we set out to cover today. We've talked about hardware failover at the server level, at the site level, clustering and AGs there, reporting servers, great way to scale out. Everybody should try to do that. Then we talked about some of the more complicated options, data-dependent routing, which few people talk about. That's the featureless version where you do everything in your app. DPVs and other assisted scale-out versions, lots of beautiful options there. And then for the supersized systems, workflow partitioning, how you design those really big apps. For each one of those, we looked at best practices, what works and what doesn't, some of the things you want to look at. My go-to for you guys is, again, like we talked about at the front, compete like water. Wherever your system is today, it's mission critical on some level. If you can affect the hardware, give it a multiple site failover, give it another server, move it into some kind of scale out, do what you can, make them better. That's our job, to guide our management and our companies and make these things rock solid. Thank you very much. Let's move to questions.
Wonderful. Now's a great time to submit your questions if you have any. One of our questions is there a way to configure a reporting server nearly real time without using high availability groups?
Yes, so absolutely, there are many ways. Transactional replication springs immediately to mind. If you need it within seconds, that's going to be your option. Log shipping is another very good option, still around. From time to time, people talk about it being decremented. It wasn't a feature originally developed by the SQL dev team. This was actually written by customers, productized by Premier Support Services, so don't necessarily worry about it going away. You can use your backups in certain situations. You can use ETL. You can use disk mirroring. So if you have a SAN or a NAS, they support disk mirroring options. All of these work. Just remember, one copy of the truth. There's a reason I spent some time on that. You can absolutely make copies of these things many different ways. You can get it over to another server. You can get it over to another set of disks. What you have to remember is you can only read from it. And that doesn't mean that you can't use that. You can run a very complicated query over there and decide this is the one row I need to go update. And then at the application level, you can submit that back into the master copy, the one copy of the truth. All you need to do is check if any of the underlying data changed, for example. But you have a ton of options. So again, if you need to be very quick, you're looking at some form of replication. If it can be slower, you have a lot of different log-based options. Also remember you have hardware options. Good question.
Awesome. I don't have any other questions yet. I'm hoping that some more will come in. But they, you know, you did such a great job. It was so thorough. I can understand why there's no questions. Just give people a few more seconds. Is there anything else that you wanted to cover really quick, or?
Well, I could talk about this for days. You know, there's like a 4-day class that I do on this. But again, the main thing is just to think about it and say, what can we do at our hardware level? Great. You know, do we have a server failover? What can we do at a server failover level? Great. Do we have a remote site? What can we do at the site level? Awesome. Do we have virtualization? What can we do to get some virtualization embedded in our SQL Server database environment? Great. Now that we have that, let's talk about scale out. What would it take to begin to scale this out? The reporting server, the application level has to route certain work to the reporting server and certain work to the database server. And so that concept to devs can be very alien. It can be a very interesting conversation of, what do you mean I have to think about whether the user is going to update it or not, and then I have to route it to server B if it's just a query and server A if it's not. SQL Server Reporting Service is a very wonderful product if you haven't used it. That's where you can spend some time and create custom reports. If you haven't done it, it's very easy. It's all HTML based. It's beautiful. So you've got a wonderful upgrade path. It's an opportunity for you, if you're a DBA, to sit down and say, what does my management care about? Or what do my customers care about? What do my database app customers care about? And you can create a couple dashboards, and they love, both of those groups love dashboards. And those dashboards can run, very easily be created out of SQL Server Reporting Services, run off your reporting server without really having any effect there. And that can become an entire business for you. And in some cases, a job-saving business.
Well, and even if you're not great at building them in Visual Studio, if you use that Report Builder 3.0, it makes them so easy and fast to develop those reports.
Yes,
I don't know if you've ever used that, but it's awesome.
I love it, and I'll give you another trick. The SQL Server itself, a lot of like weight stats and a lot of these other reporting dashboards that we have, there's about 16 in SQL 2012, goes up all the time. They are done in Report Server. So you can actually go and look at that implementation and often cut and paste it and get the same chart that they have up in your web page very quickly.
Oh,
right?
That's
and
cool.
It will just pull, it actually will pull from your SQL Server system tables. So you don't have to worry about it in the back end. It's just nice. And you can get some fantastic drill through data up there, which performs great, right? Anything in the SQL system tables, just very nice, already there, already updated, really powerful data up there.
Very cool. Okay, we probably should wrap this up. Can you go ahead and progress to the next slide? Thank you for attending the Art and Science of Designing a Mission-Critical SQL Server. I'd like to thank Maxwell for his time and his expertise. Again, I'd like to also thank our presenting sponsors, Microsoft, Cisco, and Dell Software, and our supporting software, SQL Century, HP, and SolarWinds. We hope you enjoyed this session as much as we did. Follow along on social media with @past24HOP and share your thoughts on the event with hashtags past24HOP and SQL Pass. Next slide. Stay tuned for our next session, SSAS Design and Performance Best Practices with Alan Faulkner, happening in a few minutes. Thanks so much, Maxwell.
Thanks, Andrea. Thanks, Elizabeth.